to say very much more about question 2, part 2, because the rest of it was basically exactly the same. We did the case of the norm 4, and for 22 and 121, you do exactly the same thing. You show that if r equals st, then the norm of r has to be the norm of s times the norm of t. And because of the previous part of the question, if the norm of s times the norm of t equals, if the norm of s times the norm of t equals 22, we can't have either of these being 2 or 11, so one of them must be 1. And likewise, if we're 121, neither of these can be 11, so they must be 1 and 121, which means that one of them must be 1, which means that one of s or t has to be a unit. By the way, quite a lot of people seem to have the right idea for this, but didn't write it down very clearly. So that's something to think about. Right. So for the next part of the question, you're asked to find the norm of 3 plus root minus 13. Most people seem to be able to do this. So you square that, and then you add 13, which is 22. Technically, you take the modulus, but we know that these are both positive, so the modulus doesn't do anything. So the point is, that was question 3, this is supposed to help you in the next question. All of this is leading up to showing that z root minus 13 is not a unique factorization domain, because we can find 2 different factorizations of 22. So the first one is 2 times 2 times 11, and curiously that's the one that many people didn't see, which is quite interesting, because you all know that 22 is 2 times 11. But somehow when you're doing this, you're thinking on a different level and you might not notice the obvious thing. So this is 2 times 11, which is a factorization of 22. And we know it's in irreducibles because we showed in the first part of the question that these two, wait, which part of the question? Well, these two, this has norm 4 and this has norm 121, so they must be irreducible. So the norm of 2 is 4, the norm of 11 is 121, so irreducible. But another thing we can do is we can use this norm, right? We know that the norm of 3 plus root minus 13 is 3 plus root minus 13 multiplied by 3 minus root minus 13, and that equals 22, right? And we know that these are both irreducible because the norm of this is, well, it's 22, which means it must be irreducible. So the norm of this is 22, so it's irreducible, and the norm of this is 22, so it's also irreducible. And so we've got that 2 times 11 equals 3 plus root minus 13 multiplied by 3 minus root minus 13. That's 2 different factorizations of 22. Are they really different? Oh, factorizations into irreducibles. Are they really different? Are they really, 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 really different? Well, what we have to check is that they're not associates of one another. Okay? But we know that they're not associates of one another. What does that mean, by the way? It means that can we multiply these by units to get these? Well, we can't possibly multiply these by units to get these because they've got completely different norms, right? If we could multiply them by units to get each other, then they'd have the same norms because the unit has a norm 1. So another way of thinking about it is that the only units in here are plus or minus 1, and that's clearly not, 2 is clearly not plus or minus that, or plus or minus that, and nor is 11. So we can also say that these are not equivalent factorizations. Since 2 and 11 are not associates of 3 plus root minus 13, or indeed 3 minus root minus 13. So this shows that z root minus 13 is not a unique factorization domain. Now, question 3 asked you whether it's possible for S to be a subring of a unique factorization domain but not be a unique factorization domain. Okay. So if we have S a subring of R, if R is a unique factorization domain, well look, this example has already given us an example that shows that this doesn't have to be true. So for example, we've got Z root minus 13, but it's a subring of the complex numbers, or if you like, it's also a subring of the Gaussian integers. And each of these are unique factorization domains, but this is not a unique factorization domain. And so it is possible for S to be a subring of a unique factorization domain without actually being one itself. Now you might think this is a bit strange, because surely you might think that factorization in one place is the same as factorization in its subring. But here's the point, okay? The point is that some irreducibles in here, you can be irreducible in here without being irreducible in here. If we look at the example that we had, which was this times that being equal to 2 times 11, that gave us non-unique factorization into irreducibles. But what's to say that those irreducibles were actually irreducibles in this ring? So those factorizations did both live in the big ring, but they weren't factorizations into irreducibles, so it didn't count as a non-unique factorization. So if you think about it, in the integers we have unique factorization into primes, but we don't have unique factorization. So for example, 12 equals 3 times 4, but also equals 2 times 6. So in Z, 12 equals 3 times 4, but also equals 2 times 6. That does not mean this is not a UFD. This doesn't count as a non-unique factorization. This does not count as non-unique factorization for the simple reason that these aren't all primes. Okay? So that's the moral of that story.